Welcome. In this session, we'll tackle LeetCode problem number 811, subdomain visit count. This interesting problem involves breaking down domain names into subdomains and calculating their visit counts. Let's dive in and explore how to solve this step by step. In this problem, we are tasked with analyzing a list of strings called domains. Each string in this list represents a domain name paired with the number of times the domain was visited. The format is straightforward. The string starts with the visit count, followed by the domain name. For example, 9001 discuss.leetcode.com tells us that discuss.leetcode.com was visited 9001 times. Now, what makes this interesting is that we're not only concerned with the given domain but also its subdomains. A subdomain is any domain you can derive by removing portions from the leftmost side of the domain. For instance, the subdomains of discuss.leetcode.com would include the full domain discuss.leetcode.com, the shorter subdomain leetcode.com, and finally the top-level domain com. Your goal is to calculate the total visit count for each domain and subdomain and then return the results in the same format, where each string is written as visit_count domain. The output of the problem is a list of strings formatted as visit_count domain, where each entry represents the total number of visits for that specific domain or subdomain. Let's look at an example to understand this better. Suppose the input list is domains equals 9001 discuss.leetcode.com. Here, the domain discuss.leetcode.com was visited 9001 times. Since discuss.leetcode.com is part of the larger domain hierarchy, its subdomains are also considered to have the same visit count. This means that LeetCode.com was also visited 9001 times, as was the top-level domain com. So, the output of this example is a list with the following entries: 9001 discuss.leetcode.com, 9001 leetcode.com, and 9001 com. Each of these represents the aggregated visit counts for their respective domains. Additionally, the example illustrates that all subdomains inherit the visit count of their parent domain. For the domain discuss.leetcode.com, we calculated that leetcode.com and com also had 9001 visits each, alongside the main domain itself. Let's now consider a more complex example to deepen our understanding. If the input is domains equals 900 google.mail.com, 50 yahoo.com, 1 intel.mail.com, 5 wiki.org, we need to process each domain and its subdomains separately. Starting with 900 google.mail.com, we see that google.mail.com was visited 900 times, which means that mail.com and com also received 900 visits each. This cascading effect ensures that all relevant subdomains are accounted for. The final output will include these counts, along with the results for the other domains in the input list. Let's break down the remaining domains from the previous example. For 50 yahoo.com, the domain yahoo.com received 50 visits, and its top-level domain com also inherits those 50 visits. Next, for 1intel.mail.com, the domain intel.mail.com was visited once, which means mail.com and com each receive one additional visit. Finally, for 5wiki.org, we see that wiki.org was visited 5 times, which also applies to its top-level domain org. Once we sum up the visits across all the provided domains, we get the following totals: google.mail.com has 900 visits, mail.com has 901, 900 from google.mail.com and 1 from intel.mail.com, and com has 951 visits in total. Additionally, yahoo.com has 50 visits, intel.mail.com has 1 visit, wiki.org has 5 visits, and org has 5 visits. When we compile all these results, the final output list includes every domain and subdomain along with their respective visit counts. For instance, we see entries like 901mail.com, 951 com, 50 yahoo.com, and so on. It's worth noting that the order of the entries in the output list doesn't matter, as the problem doesn't specify any sorting requirements. Now, let's review the constraints of the problem. The input list domains contains between 1 and 100 strings. Each string strictly follows the format of visit_count domain, where visit_count is an integer between 1 and 10,000. The domain name itself is composed of lowercase English letters, digits, and dots, without consecutive dots or dots at the beginning or end. These constraints help ensure that the input is well structured and manageable. To further clarify the problem, let's consider some edge cases. In the first case, we have a single domain with no additional subdomains. For example, if the input is 100example.com, the output will include 100example.com and 100com, since example.com and its top-level domain com received the same number of visits. Another scenario involves multiple visits to the same domain, such as 300example.com and 200example.com. Here, the visit counts are summed, resulting in 500example.com and 500com. Finally, we might have domains with no subdomains, like 50com, where the output simply mirrors the input. Additionally, we must handle cases where the visit count reaches its maximum value, such as 10,000a.com, which would result in 10,000a.com and 10,000com. These examples demonstrate the range of inputs you might encounter and how the solution should handle them. To tackle the subdomain visit count problem, we begin by considering the brute force approach. The intuition here is straightforward: iterate through each domain entry, break the domain into its subdomains, and keep track of the visit counts for each subdomain. This can be achieved by using a dictionary, which allows us to store and update the visit counts efficiently. The steps are simple. First, parse each entry in the input list to separate the visit count from the full domain. Then, split the domain into subdomains by using the dots as delimiters. Finally, for each subdomain generated, increment its count in the dictionary. While this approach is intuitive and effective, it has some limitations. The time complexity is n*k, where n is the number of entries and k is the average number of subdomains per domain. The space complexity is U, where U is the number of unique subdomains. Despite being straightforward, this method doesn't leverage additional optimizations to avoid redundant operations, which could make it less efficient in some scenarios. Building on the brute force approach, we can optimize it further without changing the fundamental strategy. The optimized approach retains the same time complexity of n*k, but it minimizes overhead by streamlining operations. For example, instead of performing redundant string processing, we can update the counts for subdomains directly as we split the domain. Additionally, tuple unpacking can make parsing each entry more efficient. While this doesn't reduce the overall complexity, it does make the implementation faster and cleaner. We also considered an alternative sorting-based approach where all subdomains are generated, sorted, and aggregated in a single pass. However, this introduces a sorting step with a time complexity of n*k*log n*k, making it less efficient compared to the dictionary-based approach. Sorting adds unnecessary computational overhead, making it a suboptimal choice for this problem. The dictionary-based counting approach was chosen as the most effective strategy for solving this problem. There are a few key reasons for this. First, each domain can naturally be decomposed into its subdomains, and the visit count for the full domain can be applied to all its subdomains. For example, the domain discuss.leetcode.com can be split into com, leetcode.com, and discuss.leetcode.com, and each needs to accumulate the same visit count. Using a dictionary allows us to perform constant time updates for each subdomain, which is critical for maintaining efficiency. The overall problem size, measured in terms of the number of domains and subdomains, is manageable within the n*k complexity of this approach. The simplicity and direct nature of this solution are what make it stand out. Sorting-based alternatives, though possible, introduce unnecessary complexity without offering significant benefits. While there are trade-offs, such as potential memory constraints if the number of subdomains becomes excessively large, these are rare in the context of this problem. If stricter memory constraints were required, we might explore data structures like tries, but these would add significant implementation complexity. The final algorithm for this problem is both simple and efficient. We start by parsing each string to extract the visit count and domain. Then, we split the domain into all possible subdomains. For each subdomain, we use a dictionary to store and update the visit counts. Once all entries are processed, the dictionary is converted into the required output format. This approach achieves a balance between simplicity, efficiency, and clarity, making it the ideal solution for the problem. By leveraging the dictionary for constant time updates and keeping the logic straightforward, we ensure that the algorithm performs well within the given constraints. In this problem, we are tasked with calculating the total visit count for each subdomain from a list of strings. Each string specifies a visit count followed by a domain name, such as 9001discuss.leetcode.com. The challenge lies in breaking down each domain into its subdomains and aggregating the counts for all occurrences of each subdomain. To tackle this, we start by parsing the input list. First, we initialize an empty dictionary called domain_counts to store the cumulative counts for each subdomain. Then, we iterate over the input strings, splitting each one into two parts: the visit count, which we convert to an integer, and the domain name, which remains a string. For example, the string 9001 discuss.leetcode.com is split into count equals 9001 and domain equals discuss.leetcode.com. This parsing step sets the foundation for extracting and processing subdomains. Once we have the parsed domain and count, the next step is to extract all possible subdomains from the full domain name. By splitting the domain name by the dot separator, we can isolate its individual parts. For instance, splitting discuss.leetcode.com results in the list discuss, LeetCode, com. From this, we generate subdomains by concatenating the parts from right to left. This produces the subdomains com, leetcode.com, discuss.leetcode.com. After generating the subdomains, we update the visit counts in our dictionary domain_counts. For each subdomain, we either add the count to its existing value in the dictionary or initialize it with the current count if it doesn't already exist. Finally, we format the output. We loop through the dictionary and construct strings in the format count subdomain, appending each to a result list. This systematic breakdown ensures every subdomain is processed correctly, and their counts are aggregated efficiently. Key insights here include understanding the hierarchical nature of domains, leveraging dictionaries for efficient counting, and using string operations to manage subdomain extraction. To implement this solution effectively, we rely on two key data structures. First, the dictionary domain_counts serves as our main storage for subdomains and their cumulative visit counts. This structure provides quick access and updates, which are crucial for an efficient solution. Second, we use a list, result, to store the formatted output strings. This list is returned as the final result after processing all input domains. From a complexity perspective, the algorithm is designed to handle large inputs efficiently. The time complexity is O, n*m, where n is the number of input strings and m is the average number of subdomains per domain. This accounts for the cost of splitting domains and updating the dictionary. The space complexity is O, k, where k is the total number of unique subdomains. This reflects the storage required for the dictionary entries. Together, these data structures and complexity considerations make the algorithm both effective and scalable. Let's walk through an example to see the algorithm in action. Suppose the input is 9001 discuss.leetcode.com, 50 leetcode.com, 1 com. First, we process the string 9001 discuss.leetcode.com. Splitting this domain produces the subdomains com, leetcode.com, discuss.leetcode.com. We update domain_counts accordingly, setting com 9001 leetcode.com, 9001 discuss.leetcode.com, 9001. Next, we handle 50 leetcode.com, which generates the subdomains com, leetcode.com. Adding the count updates the dictionary to com 9051 leetcode.com, 9051 discuss.leetcode.com, 9001. Finally, we process one com, which updates the count for com to com 9052 leetcode.com, 9051 discuss.leetcode.com, 9001. By the end of this step-by-step execution, all subdomains have their visit counts aggregated correctly in the dictionary. The final output is derived by formatting the entries in domain_counts into the required format count subdomain. For our example, this results in the list 9052 com, 9051 leetcode.com, 9001 discuss.leetcode.com. This output correctly reflects the total visit counts for all subdomains. A few edge cases are worth noting. If the input contains only one subdomain, such as 300 com, the algorithm handles it seamlessly. Similarly, large visit counts, such as 10 to the power of 6, are processed without issues thanks to Python's support for arbitrary precision integers. For an empty input list, the output will simply be an empty list. These considerations ensure the solution is robust and handles a wide range of scenarios effectively. This Python implementation solves the LeetCode problem number 811, subdomain visit count. The function subdomain visits takes a list of strings as input, where each string contains a visit count followed by a domain name. The goal is to calculate the total visit counts for each subdomain present in the input list. Step-by-step explanation. 1. Initialization. First, we initialize an empty dictionary domain underscore counts to store the cumulative counts for each subdomain. The keys are subdomain names, and the values are their respective visit counts. 2. Processing input. We iterate through each entry in the domains list. Each entry is split into two parts: count, the number of visits, and domain, the domain name. The count is converted into an integer for numerical operations. 3. Subdomain generation. The domain name is split into parts using the delimiter. For example, discuss.leetcode.com splits into discuss.leetcode.com. Using a loop, we generate all possible subdomains starting from each segment. For instance, the subdomains for discuss.leetcode.com are discuss.leetcode.com, leetcode.com, com. For accumulating counts, for each generated subdomain, we update its count in the domain underscore counts dictionary. If the subdomain already exists in the dictionary, we add the current count to its existing value. Otherwise, we initialize it with the current count. 5. Formatting the result. Finally, we construct the result list by iterating through the dictionary. Each entry is formatted as a string in the form count domain, where count is the number of visits and domain is the subdomain name. 6. Return the result. The result list is returned as the output of the function. This implementation handles edge cases such as single segment domains, e.g., com, or very large counts efficiently. The time complexity is approximately n*m, where n is the number of entries and m is the average number of subdomains per entry. Here, we begin by importing the necessary packages and defining our class and method. The method takes an array of strings called domains, each representing a count pair domain. First, we create a hash map to store the subdomains as keys and their respective visit counts as values. Next, we iterate over each domain entry in the input array. Each entry contains a count and a domain, separated by a space, so we split the string to extract these components. The count is converted into an integer, and the domain is further split on dots to break it into subdomains. Using a loop, we construct all possible subdomains by joining the parts from the current index to the end. For each subdomain, we update its count in the map by either adding to the existing count or initializing it if it doesn't exist in the map yet. This ensures that all subdomains are accounted for with their respective visit counts. After processing all the input entries, we prepare the result list to return the formatted output. To do this, we iterate through each entry in the domain counts map. For every subdomain and its corresponding count, we create a string in the required format, the count, followed by a space, and then the subdomain. We add each of these strings to the result list. Finally, the method returns this list, which contains the visit counts for all subdomains in the desired format. This approach ensures that we effectively handle all subdomains and their visit counts in a concise and efficient manner. In this problem, we are tasked with analyzing a list of strings where each string represents the number of visits to a specific domain. Our goal is to compute the total visit count for every subdomain and return the results in the format count domain. To better understand this, let's look at the example input, 9001 discuss.leetcode.com. First, we initialize an empty dictionary called domain underscore counts to store the aggregated counts for each subdomain. Then, for the given entry, we split it into two parts, the count, which is 9001, and the domain, which is discuss.leetcode.com. The count is converted to an integer so it can be used in calculations. This sets the stage for processing the subdomains of the given domain. Next, we break the domain discuss.leetcode.com into its subdomains. This involves splitting the domain into parts, discuss, LeetCode, com. Then, we iterate through the subdomains starting from the most specific to the most general. For the subdomain discuss.leetcode.com, we add the count of 9001 to our domain underscore counts dictionary. Moving up one level, the subdomain LeetCode.com also receives the count of 9001. Finally, the top-level domain com gets the same count added as well. This ensures that all levels of the domain hierarchy are accounted for. After processing, the domain_counts dictionary contains the counts for all subdomains. To generate the final result, we convert this dictionary into a list of strings, each formatted as count domain. This gives us the output 9001discuss.leetcode.com, 9001leetcode.com, 9001 calm for the given input. Now, let's consider a more complex example where the input contains multiple entries, some of which share common subdomains. The input is 900google.com, 50mail.google.com, 1 calm. Again, we start by initializing an empty domain_counts dictionary. For the first entry, 900google.com, we split it into the count 900 and the domain google.com. We process its subdomains, starting with google.com and adding 900 to the dictionary. Then, for the top-level domain com, we also add 900. This updates the dictionary to google.com, 900, calm, 900. For the second entry, 50mail.google.com, we follow a similar process. The count 50 is extracted, and the domain mail.google.com is processed. Starting with mail.google.com, we add 50 to the dictionary. Then, moving to the next subdomain, google.com, an additional 50 is added to its existing count. Finally, for the top-level domain com, we add 50 more. At this point, the dictionary is updated to google.com, 950, calm, 950, mail.google.com, 50. For the third entry, 1 calm, we add 1 to the count associated with calm, bringing its total to 951. After processing all entries, we format the dictionary into the output 950 google.com, 951 calm, 50 mail.google.com. In the next example, we handle an edge case where the input contains single-level domains. The input is 500yahoo.com, 300 calm. As usual, we start with an empty domain_counts dictionary. For the first entry, 500yahoo.com, we split it into the count 500 and the domain yahoo.com. Adding 500 to yahoo.com updates the dictionary. Then, for the top-level domain com, we also add 500, resulting in a dictionary of yahoo.com, 500, calm, 500. For the second entry, 300 calm, we add 300 to the count 4 calm, bringing its total to 800. This example highlights how the solution handles domains without deeper subdomain hierarchies effectively. To generate the final output for this example, we format the domain_counts dictionary into a list of strings. Each entry in the dictionary is converted into the format count domain. This gives us the result, 500yahoo.com, 800 calm. Reflecting on the solution, we see that leveraging a dictionary to store subdomain counts ensures efficient aggregation. Breaking domains into subdomains and iterating through them guarantees that all levels of the domain hierarchy are included. The time complexity of this approach is O, n*m, where n is the number of entries and m is the average number of subdomains per domain. The space complexity is O, U, where U is the number of unique subdomains. This makes the solution both effective and scalable for a wide range of input sizes. The time complexity of our solution depends on the operations we perform on the input list domains. First, we iterate through the list, which has n entries, each formatted as a string-like count domain. This initial iteration requires O, n, time. Next, for each string, we use the split operation to separate it into two parts, the count and the domain. If the length of a string is m, this operation takes O, m, time. Across all entries, the total time for splitting is proportional to the combined size of all strings in the list, which we denote as s. Finally, we further split each domain into subdomains using the split operation. If a domain has k substrings, this operation takes O, k, time. Summing over all domains, this step is also bounded by O, s, as the total size of the strings dominates. These steps give us a foundation for understanding the time complexity of our solution. Once the domains are split, we generate subdomains and update their counts. For each domain split into k parts, we create subdomains by joining these parts in k iterations. The operation .join takes O, k, time in the worst case, resulting in OK squared for a single domain. However, across all domains, this cost is bounded by OS, as the total string size dominates. Updating the count for each subdomain in a dictionary is an O1 operation, so processing all subdomains collectively also takes OS. Lastly, when formatting the output, we convert the dictionary domain underscore counts into a list of strings. If there are D distinct subdomains, this step requires OD time. Each of these components contributes to the overall efficiency of the solution. Now, when we combine all these steps, we can summarize the total time complexity. Iterating over the domains list takes O(n). Splitting strings, generating subdomains, and updating counts collectively require OS. Formatting the final output adds an additional OD. Since the total size of all strings, S, is the largest contributor and dominates both N and D, the overall time complexity of this solution is OS. This makes the solution efficient, especially for large inputs with many subdomains. The space complexity of this solution is primarily determined by the storage requirements for the dictionary, the input, and the output. The dictionary domain underscore count stores counts for each unique subdomain. In the worst case, all subdomains are unique, so if there are D distinct subdomains, the dictionary requires OD space. Each key in the dictionary is a string, and each value is an integer, so the total space used is proportional to the combined size of all unique subdomains. The input list domains itself occupies OS space, where S is the total size of all strings. Similarly, the output list requires OD space, as each entry corresponds to a distinct subdomain. Temporary variables like subdomains, entry, and count require negligible space compared to the input and output. Together, these components define the space usage of the solution. In total, the space complexity of the solution is OS plus D, where S is the total size of all strings in the input, and D is the number of distinct subdomains. This is efficient given the constraints of the problem. Comparing this to a brute force approach, where we would recalculate subdomains repeatedly and count occurrences redundantly, the naive solution would have a much higher time complexity of n*k squared, or worse, where k is the average number of subdomains per domain. In contrast, our optimized approach avoids redundancy by directly storing counts in a dictionary and reusing previously computed subdomains. This reduces the time complexity to OS and ensures optimal performance. Overall, the solution achieves a time complexity of OS and a space complexity of OS plus D, making it significantly more efficient than a brute force alternative, especially for large datasets with repeated subdomains. When working on the subdomain visit count problem, there are a few common mistakes to watch out for. First, many people forget to split the domain string into all possible subdomains. For instance, given the domain mail.google.com, you need to count visits for mail.google.com, google.com, and com. Failing to do so leaves out some subdomains, leading to incomplete results. Another frequent issue is using inefficient data structures, such as lists, to track subdomain counts. A dictionary is a better choice since it allows for O1 average time complexity for both lookups and updates, whereas lists could degrade performance to ON. Finally, skipping edge cases is a critical mistake. You need to handle scenarios like empty strings, single-level domains such as com, or malformed input like 123. Ignoring these can result in runtime errors or inaccurate outputs, so always ensure your solution accounts for such cases. Another challenge arises when parsing the input correctly. Misinterpreting the input format, such as failing to separate the visit count from the domain string or mishandling whitespace, can lead to incorrect domain parsing and ultimately wrong results. Similarly, pay close attention to how you construct subdomains. Off-by-one errors in slicing or indexing often occur, such as accidentally excluding the top-level domain or including invalid characters. These errors result in missing or incorrect subdomains being processed. Accurate parsing and indexing ensure that your solution handles the problem as intended and maintains consistency in the results. From an interview perspective, this problem is a great way to showcase several key skills. First, it involves recognizing patterns, particularly the hierarchical relationships between subdomains, which is similar to breaking down file paths. Interviewers often look for your ability to break the problem into smaller, logical components and handle related entities. Additionally, choosing the right data structure is critical. Using dictionaries, or hash maps, demonstrates an understanding of how to achieve efficient lookups and updates. Always clarify input constraints to ensure you're handling edge cases properly, such as malformed or irregular inputs. Lastly, be prepared to discuss scalability. Explain how your solution can handle large datasets, such as millions of domain entries, to show you understand the trade-offs involved in your approach. This problem connects to several others that can help strengthen your understanding. For example, problem 811 itself can be practiced with variations in input formats or constraints to deepen your familiarity. Problem 49, group anagrams, involves mapping keys, such as sorted strings, to groups of values, similar to the mapping of subdomains to counts. Problem 347, top k frequent elements, focuses on counting frequencies and retrieving the most common items, which is a useful skill for frequency-based problems. Lastly, problem 953, verifying an alien dictionary, tests string manipulation in sorting logic, which parallels the subdomain parsing required here. Alternative approaches to the problem can also be explored. A tree-based solution, for instance, involves building a hierarchical data structure where each node represents a subdomain and stores its visit count. While this uses more memory, it can be effective for hierarchical queries. Another approach is pre-processing optimization, where all possible subdomains are pre-computed to reduce repeated parsing. This can save runtime for repeated domains but comes with its own pre-processing overhead. A final approach to consider is sorting the input by domain name. Once sorted, you can iterate through the group subdomains to compute their visit counts. This method simplifies processing by grouping related domains together, but it introduces an O(n)log(n) sorting overhead. While this may not be the most efficient choice for unordered counts, it can be practical for scenarios where grouped operations are required or if sorted results are needed. As always, understanding the trade-offs and choosing the best approach for the problem's constraints is key. Great job! To wrap up, we reviewed how to use hash maps and string manipulation to solve this problem efficiently. Understanding problem requirements and choosing the right data structures are key takeaways. Thanks for watching, and stay tuned for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!